So you have me back. I'm sorry about that. Pretty sure that you would prefer Alison for the rest, but well, that's the way it is. So I understand that you covered Bayesian learning and prediction, right? Is that correct? So what we will cover this week is chapter 5, which is Bayesian inference and has to do with utility and decisions. What we will do is to very loosely formalize the inference process from a Bayesian perspective. So far, we've managed to update our initial knowledge on the prior using the data and obtain a posterior distribution. And we also have, if we wanted to, a predictive distribution that we can use for forecasting. Okay? And from a Bayesian learning point of view, that is the end of the story. We end up with a distribution, a probability distribution that describes our state of knowledge, which takes into account all the different sources of information that we have. So we have a prior if we don't have any data. We have a posterior if we're interested in the parameters given the data. We have a predictive if we're interested in doing some sort of forecasting. But usually we would like to do something with this distribution, right? Usually statisticians are approached by scientists, by economists, whatever, in order to give them an inference, to say something about the quantity of interest. This could be a parameter, or it could be a forecast. So if you give them back a probability distribution, they probably won't be very happy. They would like to make a decision with that data. We would like to know where the parameter is likely to be, or whether you have a forecast that they can then contrast with experiments. Okay? And that is inference. So just as I tried and do with prior information to make a point that information is subjective, inference is also subjective. It depends on what you're using or what are your objectives in doing inference. And this example is hopefully pointing in that direction. Okay? So we have two possible decisions, two possible scenarios, if you wish. You have a headache, and you're considering to take a painkiller. Okay? And you read the little leaflet there, and apparently there's a 1 in 20 chance that you will get an upset stomach. Okay? Now, for us that don't have very good eyesight, you're considering having laser eye surgery, and you're told that there is a 1 in 20 chance that if you take the surgery, you will go permanently blind. Okay? The distribution, the relevant probability distributions are exactly the same, right? The probability of a bad consequence is basically the same, right? I would definitely not doubt to take the first decision. I would take the chance of having an upset stomach if that would stop my headache. But 1 in 20 chance of going blind if I take the surgery, probably I would definitely consider that very, very slowly. So that's what we mean. The consequences of our decisions should come into the inference stage. Okay? So we have used Bayes' theorem to update our beliefs, to update our knowledge about the parameter or parameters. So what do we do with this posterior distribution? Okay? And from a Bayesian perspective, that is making decisions, so making a decision on how we use that information in the relevant distribution under uncertainty, because obviously we do not know for certain what is the value of the parameter or what is the value of the forecast that we want to make. Okay, so we need to formalize somehow this decision making under uncertainty and frame that into the inference problem. And normally in inference we have three basic problems. We want to do either point estimation, interval estimation, or hypothesis testing, right? So what we need to do is to set up, and I will do it very loosely, a decision framework that will allow us to provide those inferences using our main tool, which is the relevant distribution that we have. Okay. So again, to make this formal, I've already talked about when you want to make a decision, you need to take into account the probability of the event or whatever the quantity you're talking about, just like the 1 in 20 chance of having an upset stomach or going blind, but also you need to take into account the consequences of that decision, right? And that's what we're going to do. So we'll introduce a function that will measure the consequences of the decision that we take, okay? And that decision will depend on the state of the world, basically the parameter that is unknown, okay? So that is the basic framework that we're going to talk about, okay? So in order to measure the consequences of any decisions that we make, we will introduce a utility function. And this utility function is a function of your status, your state. So what happens? You take the pill and you have an upset stomach. You take the surgery and you go blind. Okay, so that is your state. What is the utility of being without a headache, without upset stomach, or what is the utility of being blind? Okay, so that's what we're trying to measure. So this utility, just as our information, we're Bayesians, is subjective. Okay, so this utility reflects numerically how that state is, how desirable, that state is for you. Okay, and one of the important things about this utility measure or function is that we need this to be linear. Okay, we want this utility to tell us that if state A is twice as preferable as state B, then that utility value, the utility value that we apply to these two states, is twice as big. Okay. In practice, sometimes it's common to equate this utility with money. Probably if you've heard news about the NHS, they have this nice scheme that basically does that. It measures how beneficial some procedure can be in society, how much it costs, and comes up with a value, a nice value. And based on that value, they decide whether that procedure is offered in the NHS or not. Okay? So that kind of thing is done routinely in practice, and most of the time it involves some measure or some monetary measure. But I will come up with an example in a minute that will highlight at least that utility and money is not exactly the same thing. Okay? It depends on the scale that we're talking about. Okay? But anyway, so that's what we will try to do. We'll try to come up with a utility function that will tell us how desirable one state is to another. That state will depend on the quantity of interest, either the parameter or the value that we want to forecast. And then we will use that to decide how to make inference. Okay? So just again, introducing some notation that, again, is just loosely formalizing this process. So D, small d, is the decision that we make. And this D lives in the set of all possible decisions. So again, take or not take the pill, take or not take the surgery, so on. And then your status depends on the decision that you made, okay? So if you were able to describe all the possible decisions that you can make and then attach a utility, and then know which state you would be after making that decision, and then attach a utility to that, then you can directly compare the utilities of different decisions, and obviously you will take or make that decision that will yield the highest utility, right? It's kind of obvious. The problem is that we do not know what the value of the parameter will be, right? So we cannot know for certain what state we will be in, because that state depends on the parameter, okay? So what we will try and do then is basically to maximize the expected utility. What we know about the parameter or the quantity of interest is described in the relevant distribution. So we will use that distribution to take the expected utility, and then we will try to maximize that expected utility. Okay? That's what we're going to do. And this is a convention in Bayesian statistics. We usually work with losses instead of utilities, but that's just a convention. That's basically just, instead of maximizing the utility, we minimize the negative utility. Okay? And what we will be doing as Bayesians is to minimize the expected loss. Okay? And that will be the process. We will have a loss function instead of a utility function. We will try and calculate the expected value of that utility function, of that loss function, which depends on the state, that is the decision that we will make, and the parameter. When we take the expectation, the parameter will disappear. So we will try to maximize that utility, that expected utility, okay? Or minimize the expected loss. So now just again to mention quickly how not necessarily money and utility are in the same scale basically. We have two decisions, right? In both we will flip a coin. The first one, you will win 10p if it comes out heads, or you lose 10p if it comes out tails, okay? The second one, you will win £1,000 if it's heads, or you will lose £1,000 if it's tails, okay? So would anyone be willing to take that one? No. Probably not. Well, at least I wouldn't. Would anyone be willing to take that one? Probably I would, right? The expected utility, the expected loss, is exactly the same under each decision, right? So you have probability 1/2 of winning, probability 1/2 of losing. The expected utility is 0 for 2. So if you're a Bayesian, you would be equally willing to take any of those, right? If your utility was measured by money. But usually, if you don't have a lot of money, large quantities will be less attractive to you if you lose large quantities. And the technical term for this is that if you prefer that bet or that decision to that one, that means that you are risk averse. and most people are risk averse. Okay. So what this means basically is that for most people at least, the relationship between utility and money is not linear. It's not necessarily linear. Okay. And well, just to mention it, if you think about that, the NHS again makes decisions based on basically money, but the money for the NHS, or the value of money for the NHS, is probably very, very different for the value of money if you're sick, right? So these kinds of measures, although they're used or they're done often in practice, might be debatable in a more individualistic basis. But anyways, that's the way it works. Okay. So again, I'm doing this very loosely because we don't want to concentrate on the theory of decision making under uncertainty. We would like to use this theory to make inference. Okay, and that's what we are trying and do now. Okay. So remember, we have three basic inference questions. We can do testing, we can do point estimation, we can do interval estimation. So we will need to set up or to come up with loss functions that are compatible with these three inference questions, right? And I will start with hypothesis testing. Okay. In general, if you want to test a hypothesis in stats, what you would like to test is whether the parameter lives in a subset of the parameter space, right? You want to analyze, to give some measure of evidence in favor of these hypotheses, okay? We want to use, obviously, the relevant distribution. In this case, I'm using the posterior distribution in order to measure this evidence, okay? And the most natural way of doing that will be to basically calculate the probability of that hypothesis under the posterior. And that's really straightforward. That's just the integral over the corresponding space of the relevant distribution, in this case, the posterior. If these probabilities are in between 0 and 1, so they have a very definite scale, so it would be relatively easy to measure the evidence in favor of any hypothesis, right? If this probability is high, if it is close to 1, then we have strong evidence in favor of that one. If that probability is close to 0, we have very small evidence in favor of that one. Okay? Now we want to bring in the consequences of deciding whether we act as this hypothesis is true or we act as if that hypothesis is not true. Okay? So this is where the loss function, the decision theory kicks in, and we will define two different decisions, right? The first decision is we will act as if the hypothesis was true. And the second is we will act as if it wasn't true. Okay? If we define these two actions, then we can come up with a possible loss function. Okay? And this is similar to errors of type 1 and type 2, if you remember that from hypothesis testing, right? So if we make decision 1, if we act as if H was true, then we lose nothing if indeed the parameter lives in that region. But then we will have a loss if that is not the case, okay? And we'll call that loss 1 just because that's linked to decision 1. If we make decision 2, then we will not lose anything if the hypothesis is false, and we will have a loss if that is not the case. Okay? And the restriction here is that these losses have to be positive, obviously. Okay? So this is a very, very general structure, and you can relate now L1 and L2 to how bad making errors of type 1 are, compared at least with how bad making errors of type 2 are. Okay? And from a theory perspective, we are all done, because we have a loss function, we have a probability distribution. The only thing we need to do now is to calculate the expected loss and compare them. Okay? So the expected loss, of decision 1 will be, if I go back, no, back is that way, will be 0 times the probability of theta being in that region plus L1 times the probability of theta not being in that one, right? And a similar calculation will yield the expected loss of decision 2 as L2 times the probability of theta being in the region. Okay? And now we just compare them. We will make decision 1, that means accept or act as if H was true, if the probability under the relevant distribution, in this case the posterior, is large enough, right? And that large enough depends on the relation between how bad we think making error of type 1 is compared to error of type 2. Okay? These two values, just as the prior probabilities, are elicited from the decision maker, right? So if you are approached by someone, you need to ask that person how bad it is to make an error of type 1, how bad it is to make an error of type 2. And in reality, what you need to assess or to elicit from them would be how bad one type of error is relative to the other, right? Once you have that, then you can, for that specific loss function, provide a decision, an inference. Okay. Don't know if I have an example. Yeah, I have an example there, just to fix ideas. We've been working with that example, the pollution data. We have, I can't remember, I think it was like 11 observations of the pollution levels at some point. And we were assuming that these pollution levels were Gaussian with a known mean and known variance. We had a prior that on the unknown mean that is Gaussian with mean 14, I believe, and precision 1. If we update our knowledge, we get a posterior distribution that is Gaussian, we know that, with mean 1539 and precision 9.33. Okay? So in the example, I think we're interested in, do I have it here? Yes. We're interested in testing whether this level of pollution is above 16, because 16 is thought to be dangerous, right? So what we are interested is in basically saying if the pollution levels are dangerous for people, okay? So we can calculate that probability quite easily. We can go to R and calculate that probability, the probability of theta being larger than 16 under this posterior, right? And that will give us an idea of how strongly the data itself suggests that the hypothesis is true. But it's not the only thing that we need. We need a loss function, okay? So coming back to our decision scheme, we have two possible decisions. One is act as if the hypothesis was false in this case, theta smaller than 16, or act if theta is larger, as if theta is larger than 16. Okay? Someone went and asked the decision maker about how badly one error would be compared to the other, and we came up with these values. So this means acting as if the pollution levels are not dangerous, right? When the pollution levels are dangerous, is 9 times as bad as acting as if they are harmful when they are not. Okay? And that kind of makes sense. You would like to be on the safe side. Okay? At least in this case. So we have, again, once we've set up our our loss function, we only need to calculate the expected value of the loss under the posterior, and that will be 9 times the probability of theta being larger than 16, and these will be 1 time the probability of theta being smaller than 16. And we just need to compare them. Okay? And it is as easy as that. Once you get these expected losses, you will make the decision that has the smallest expected loss, right? In this case, you will make decision 1, which is, if I go back, act as if theta was smaller than 16, and that means that it is safe, right? Again, if we only had the relative weight of decision 1 over decision 2, 0.9 in that case, we would be also able to make the same decision, right? Okay? So, as opposed or in contrast with frequentist testing, there are no p-values here. There are no convoluted interpretations of how to work with the p-value and what is the probability on the repeated sampling, nothing of the sorts. We have probabilities that are subjective, yes, but we have probabilities given the data. And as such, we are able to assess the evidence in favor of any hypothesis using the corresponding areas under the curve, basically. Okay. Any questions so far? Okay. So now if we move on to point estimation, in point estimation, what we would like to do is to pick one value of the quantity of interest, in this case the parameter, and quote that value as representing basically the location of the posterior distribution, right? Or the relevant distribution. Okay? So now the set of all possible decisions will be the parameter space. We can choose any value in the parameter space. Okay? And we will need to pick one of them. So we need a loss function, and in this case we will look into 3 loss functions that will allow us to attach utility to selecting each single value in the parameter space, measure that utility, and then optimize the expected utility. Okay? There are many, obviously, but we will explore 3 of them that are the ones that we use more often in practice. Okay? The first one is quadratic loss. And this loss basically tells you that the further d is your decision, that will be the value of the parameter that you will quote as your point estimation. Theta is the real value of the parameter, which is unknown. And what this loss function is saying is that the further you're away, the larger the distance between your decision and the true value of the parameter, the larger your loss, right? And that increase is quadratic. You have the derivation in your notes. It's very easy to do. But once you take the expected value of this quadratic term on the posterior distribution and then optimize that expected loss with respect to D, remember, we want the decision that makes the loss the smallest, then we can prove that the expected value of the relevant distribution is the base decision, right? So if we have quadratic loss, we haven't assumed anything else than we have a relevant distribution and the loss is quadratic. So under any possible distribution, if the loss is quadratic, the base decision, the base point estimate, will be the posterior mean. Okay? No matter what. So what this loss is saying is that if you're estimating, that means that overestimating or underestimating are penalized in the same way, right? Basically. Sometimes that is not the case. So we would like a loss function that penalizes differently overestimation to underestimation, right? And depending on the problem that we have, or depending on the preferences of the decision maker, L1 will be larger or smaller than L2. So overestimating will be more or less penalized than underestimating, okay? So this is very general. Again, the derivation of the optimal base decision is in your notes. It's not relevant. It's just for you to understand how it is done. What we are interested in is in this best decision. And in this case, the best decision, or the base decision, under these laws, is the quantile under the relevant distribution defined again by the relative sizes of L1 and L2. Okay? If, in this case, overestimating and underestimating are equally bad, so L1 and L2 are the same, then this becomes a half. And then what we have is that the base point estimate will be the median, right? That point that leaves half of the probability to the right, half of the probability to the left. Okay? Which again seems like a natural estimate or a natural measure of the location of the distribution, right? So quadratic loss, posterior mean or the relevant mean, linear loss, the quantile, in particular, if L1 and L2 are the same, the posterior median. The third loss function that is used often in practice is called the 0-1 loss, and this is you lose 0 if you're close enough to the true value of the parameter, and you lose everything, 1, if you are far away from it. Okay? And obviously we would like to make this distance as small as possible. So when that distance, when that A goes to 0, the optimal estimate is the mode of the posterior. Okay? Which again, I'm assuming that you are familiar with mode. Mode is the maximum of the distribution. Okay? The point that maximizes that distribution. We'll do an example at some point, probably tomorrow, to make it clear. Okay? But now we have 3 possible loss functions and 3 possible decisions, right? We have the posterior mean, the posterior median, and the posterior mode. Okay? Now, what happens in our example? In our pollution example, we have the relevant distribution is a normal, a Gaussian distribution, with mean 15.39, and I think the precision was something like 9.3. Gaussian distribution is symmetric. It's symmetric around the mean. So the mean is the median, and also it is the mode. Okay? And that will be the case for any symmetric distribution that it's unimodal. The base estimate under any of those three losses will be the same, will be the posterior mean. Okay? If the relevant distribution is not symmetric, if it is skew, these three values will be different. So we will need to make a decision, or even better, quote the three values. Okay? Yeah. Cool. Yeah, great. So we know we are Bayesian, so we are now used to work with uncertainty. We know that providing a point estimate is never enough. We always need to give a measure of uncertainty in our estimations. Okay? So the best way to do that sometimes is to quote an interval estimator. Okay? So what we want is an interval in our posterior distribution that has some probability content, usually a large probability content, but we want that interval to be as short as possible, right? If you think about the pollution example, for instance, we can quote any interval M star we use. Okay. That will be probably standard deviation. We can quote an infinite number of intervals that have the same probability content, right? We can say any interval of the, I will call it set Q, any interval of this shape, one-sided interval, when we chose this quantile to be the quantile that we want, we'll have that probability content, or the other one-sided interval, or we can have any number of them, okay? But what we want is intervals that have some probability content, but are short, the shortest if possible, okay? So a possible loss function for that will look like this, will be a penalty for the probability of theta naught being in the interval, and then a penalty for the width of the interval, for the length, right? You don't have the derivation in your notes because it's quite difficult, but if you optimize this loss function, fixing, say, the probability content of the interval, then you will want that interval with that probability content and as short as possible. Then you end up with what we know as the highest posterior density interval. That means in the interval you will include all the points in the relevant distribution that have highest density compared to those points not in the interval. Okay? In practice, finding highest posterior density intervals is difficult unless the relevant distribution is symmetric and unimodal. In that case, like in the Gaussian, the highest posterior density interval will be centered at the mean because that's the highest point, that's the mode, and will be a symmetric interval around that mean. Okay? In other cases, finding the highest posterior density interval will be much more difficult unless the relevant distribution is relatively simple. And again, we will see an example tomorrow. Okay? So what we do in practice is to quote the equally tailed interval, and we can always do that. If we have the relevant distribution, we can calculate the probability in the tails all the time, so we can always find those quantiles that leave 1 minus the probability that we are interested at either side, and then we will have an equally tailed probability interval. And in practice, that's what we usually do. Obviously, this equally tailed probability interval will be the highest posterior density interval if the distribution is symmetric. Okay? So let me just have a look. Yeah, just to fix these ideas. In this example, as I mentioned, the posterior density, or the relevant density, is symmetric. So the highest posterior density interval is the interval centered at the mean and with equally tailed, the equally tailed interval, sorry. Okay, so that was easy. And our next example, yeah, okay. I think I will stop with examples there because we will work them tomorrow. Yes. So, as you probably now can see, making inference from a Bayesian point of view is just finding summaries of the relevant distribution, right? So all the convoluted interpretations that you're used to in the frequentist approach, where a confidence interval has to be interpreted as those intervals that, if you repeat them a large number of times, will contain 95% of all those convoluted interpretations do not exist in the Bayesian perspective. The price to pay is that you need to think about the problem. You need to think about your prior, you need to give an assessment or elicit your prior distribution, and then you need to think about the consequences of the kinds of inferences that you want to do. Okay? So you need values for L1 and L2 if you want to do hypothesis testing, or you need to choose a relevant loss function for point estimation. Okay? But that's usually good because that means that you hopefully understand what you're doing instead of just, applying formulas. Okay? But at the end, any relevant inference will be derived from the relevant distribution, and the interpretation will be probabilistic. Okay? So we will have probability intervals. The content, you can say that the probability of the maximum pollution level given the data in this example is being in between 14 and 16.03 is 0.95, right? You can say that. And usually, in practice, that's what people understand. So it makes Bayesian inference a more natural way of conveying uncertainty in inferences. Okay? So tomorrow, we will do on the board, a full worked out example so you can fix ideas and we can follow it. Okay? See you tomorrow then.